Okay, let's start. So we began discussing cyclic structure of Fp, which is the finite field. Numbers are from 0 to p minus 1. So with addition, we saw that the addition structure is cyclic because you can generate everything by 1. Just keep adding 1 again and again. Second, more important or more interesting thing we will study is the cyclic structure of multiplication. So we will show that everything can be generated by one element. There will be an element A which will do this. That's called a primitive element. So for that we defined order. Order of an element is the least number E such that A to the E is 1. Anything else, any other n will be a multiple of E. By this Fermat's little theorem, we know that A to the p minus 1 is 1, right? So in particular, order will always be a factor of p minus 1. You get that immediately, and order of A to the k is order of A divided by the GCD. Any questions till now? Okay, so after this we can prove the primitive element existence theorem. So for prime P, Fp has phi of p minus 1 primitive elements. So we will show in one shot we will show that there is not just one primitive element, but there are many primitive elements. Okay, so if you take p to be 5, then there are phi of 4 many primitive elements. There are 2 primitive elements. And as you take bigger and bigger primes, this phi of p minus 1 is quite large compared to p. So in other words, if you just randomly pick an element from Fp, it is a primitive element with high probability. There are a lot of primitive elements. Okay, that is what we will show. So, right, so Fp star, remember, is simply Z mod P, or well, we use the finite field, so Fp minus 0. And its size is p minus 1. So if you look at the equation x to the p minus 1 equal to 0, how many elements are roots of this polynomial? Everything in Fp except 0, right? So has roots, everything has p minus 1 roots in Fp star. Every element in Fp star satisfies this equation, it's a root. So it has p minus 1 degree and it has p minus 1 roots, right? So it cannot have more, but it has exactly these many. So this equation will be the cornerstone of the proof. What we want to show is existence of primitive elements that are roots here. This is the Fermat's little theorem. If you take any element in Fp star, and you take D to be the order of the element, then A is a root of x to the D minus 1 equal to 0. Right, this is obviously the definition of order, and D divides P minus 1. Right, so that is our setting. So any ideas from this setting, how will you deduce that there are elements A for which D is equal to P minus 1? Right, you want to maximize D. The maximum it can be is P minus 1. How do you show that there will be A's with D equal to P minus 1? So what we will do is, we will count the number of roots of these equations, and we will write down some counting tricks. So let's count roots of such equations. Basic idea will be actually counting. So the trick is that you define E of D to be the number of roots of x to the D minus 1. And with this ED, you can show that if you go over all the D's, what do you get? If you pick a divisor D of P minus 1 and you count how many x's there are, satisfying x to the D equal to 1, and you sum it up over all D, the answer will be so we claim that this is P minus 1. How do you prove this? How do you show that sigma ED over D dividing P minus 1 is P minus 1? Sorry, this is, I did wrongly defined ED. It should not be this, it should be order equal to D. Yeah. Because we are interested in E of P minus 1, right? We are interested in how many elements are there with order P minus 1, maximum order. So instead of just looking at E of P minus 1, we will look at all these EDs. So what is the sum of all these EDs? It's P minus 1. So what I had written before, that would be greater than P minus 1. Now it is exactly P minus 1. So the proof is simply that, yeah, you take any element in Fp star, A contributes to unique ED. For a unique D. Okay, the reason is that you take any element in Fp star, let's say equal to 2, then where is 2 being counted in the sum on the LHS? It is being counted exactly the place where D is the order of 2. Right? Only that E of D 2 is counted, it cannot be counted in any other ED prime. So every element is counted exactly once, hence you have left hand side equal to p minus 1. That's the set, that's the number of A's, right? These are all the elements. Is that clear? So that's the first property that you get by counting. Second property that you can write is, let me call these claims. The second claim you can show is sigma phi d as you go over all the d's that divide n. This is equal to, that was your quiz question, right? That is equal to n. How did you prove it? Sorry? By induction. On what? On n. Yeah, if you multiply, yeah, so induction on the number of prime divisors. Yeah, so we can do it directly. So you just write n as product of pi ei. Pi's are distinct primes. This is the distinct prime factorization. And then left hand side is equal to sigma. So factor means that you will have smaller, possibly smaller ei primes. Right, so divisor just means that you are allowed to take anything between 0 to ei in the exponent. So that's ei prime. And now what do you do? So now you swap sigma with pi, sum with product. That's the trick you are supposed to learn in the quiz. So you can write it like this. Right, so the proof of this is that you, when you try to expand this product out, you will see that you will get all possible divisors d, right? Is that clear? And what next? What do you do with this? By the way, here we are using that this phi is multiplicative. Right, so you were proved in the class that phi of p times q is phi of p times phi of q. So we are using that repeatedly, and then you can check that this holds, which can now be written as so what is phi of pi? What is phi of pi square? So you see the pattern, right? What you are getting here is the last number, which is pi to the ei, which is equal to n. Right? That's the proof. So if you sum over all divisors, you get n for the Euler-Trojan function. That's claim 2. Any questions here? Claim 3 is that for all the d's, ed is less than equal to phi d. Let's prove this. So recall, ed was the number of elements with order d. So, consider an X or consider an A in FP star with order A equal to D. It's a root of x to the D minus 1. It satisfies this, of course. Okay, the interesting thing is, can you tell me the other roots of x to the D equal to 1 equation? If I give you A, can you find all the roots? There can be at most D roots, right? Can you find all the D roots from A? For example, is A square a root of x to the D equal to 1? Sorry? Sorry? No, just a root. Yeah, so A square is a root, A cube is a root, and A to the D is a root, right? So, A square, A cube, everything is a root of this. So let's call it fx. So if I give you an element A of order D, then it actually generates multiplicatively all the roots of x to the D equal to 1 equation of this polynomial fx. And yeah, which is non-trivial because it could have had less than D roots, but it doesn't. It has exactly D roots. And as you know, it cannot have more because we have shown that over a field, there cannot be more roots than the degree. So these are exactly the roots of fx. So let's write that. All the roots. So once you know all the roots of x to the D minus 1, can you now say which ones are which of these are of order equal to D, right? Because you are interested in E of D. So which of these roots are of order D? Right. So note that A to the K has order K divided by K comma order of A, which is D. So number of A's, number of A to the K's with order equal to order of A is D, right? Sorry. So number of A to the K's with order equal to D is number of K's such that it is co-prime to D, which is phi of D. So that comes out to be phi d, right? Okay. So what have we shown? So it seems that we have shown ED is equal to phi d, haven't we? We have shown something stronger than what claim 3 says. Do you see any mistake? Because if we have shown this, then clearly we have shown that there are phi of p minus 1 primitive elements. Because E of p minus 1 is phi of p minus 1, right? Then we are already done. So have we proved the theorem or not? What do you think? Well, since I am asking the question, clearly we haven't proved it because we haven't shown that such an A exists, right? We are saying here that if there is a A of order D, then there will also be phi d many, but maybe there is no element A of order D, right? That's possible. That exactly was the problem of primitive element also, that maybe nothing exists. So what we have shown is this is equal if A exists. If one A exists and it is 0 otherwise, right? So we have shown something better than the claim, but we have not shown equality because the only problem is this existence. If it exists, then its ED is equal to phi d. If it doesn't exist, then ED is equal to 0. Right? So you have this Boolean, you have two cases, you don't know which one. So maybe we can write this down here. So ED is equal to phi d or 0. Those are the only two cases. But it seems that we have still not made much progress because we are still in this Boolean confusion that answer can be 0 or it can be phi of p minus 1. So how do you resolve that? How do you show that there is an A? So you use the previous claims. So previous claims gives you kind of an aggregate, right? So you see that using claims 1 and 2, what you can write is, in fact, all of them will do. So p minus 1 we have shown is equal to sigma phi d. And phi d we have shown is at least sigma ed. And sigma ed we have shown is back to p minus 1, which means what? Yeah, which means that everything is equal, right? So this is a nice kind of averaging argument. Because of this aggregate, you will get that every ED is equal to phi d. So of course, the reason is that if any ED is strictly smaller than phi d, then the sum cannot be equal to p minus 1, right? So every ED has to reach its maximum, which is phi d, which means that phi of p minus 1 a, E of p minus 1 is equal to phi of p minus 1. So there are many primitive elements. Okay, as many as exactly phi of p minus 1. Is this clear? That finishes the proof of the top theorem, that for any prime p, the finite field has lots of primitive elements. Any questions? So this is a major theorem because it is not, I mean, when we define finite field, it was not clear at all. Nobody would conjecture that there will be elements that when multiplied together, when powered, can generate all the elements, right? So now if you look at mod 101, you know that there is a number which whose powers will give you everything from 1 to 101. So that's a very non-trivial number theoretic fact. Yeah, if you have any questions, you ask now, because next we will take it to another level which will be far more abstract. So if you are ready for that, only then should we move. So I consider silence as agreement. So let's move forward then. So now we will take this to the next level of abstraction, which is we'll not talk about numbers, we'll talk about polynomials and still prove the same things. Okay, we'll construct more abstract finite fields. So this idea can be generalized to more abstract constructions. And algebra is all about abstraction. So the abstraction will be that just like you started studying the modulo arithmetic, right, z modulo 2, z modulo 3 or even z modulo 4, now you study a polynomial ring modulo polynomial. So you can study now things like fpx, let's say to begin with modulo x. What is this? So here you do addition and you do multiplication and then you divide by x and take the remainder. What will you get? If you do mod x, then there is no x, right? So this will be the same as fp. Right? This is not going any further than numbers. So you can be more ambitious and you can do something like this. So what happens now? If you take a polynomial, multiply or add with something else and then do division by x square plus 1, what is the remainder that you get? You get a linear polynomial, right? Ax plus b. So this is that set. So it has the elements ax plus b, where ab are numbers, and it has addition and multiplication. Modulo x square plus 1. Right, so this is the x square plus 1, mod x square plus 1 arithmetic. So obviously you know how to add. Addition here is simple. Ax plus b with a prime x plus b prime will just be a plus a prime b plus b prime. the interesting thing is multiplication. So when you multiply, then you will get potentially quadratic term x square, and that then you will divide and reduce. So for example, what do you think is x plus 1 times x? So this is x square plus x, which is what in this arithmetic? X square is like minus 1, so you get x minus 1, right? So this is the new arithmetic, right? This is mod arithmetic but without numbers. Now you are doing it more symbolically with variables. And you will be happy to note that you can also do division. Which will not be always, but whenever, I mean, you are not doing division by 0. So what is the inverse of x here? So 1 by x is there in this arithmetic. It was not there in the polynomial ring. What is x inverse? Yeah, x inverse is minus x. Right, so it is quite simple here, but in general you can see that it will be complicated because you will do Euclid GCD, and then you can get anything, any ax plus b you can get, but here you get just minus x because you can see that x times minus x is 1. Right, this is the multiplicative inverse. So once we have generalized mod arithmetic to this symbolic abstraction, when do you think an inverse will exist? Always, except 0. Every element has an inverse, which means that this mod arithmetic gives you a field. Exactly, so that is the, when you realize that, you become intelligent, that now same concepts can be generalized. So this fpx mod f is a field if and only if fx is irreducible. In fpx. Okay, so the reason is that, I mean, you start with fx irreducible. So this is kind of the prime in the polynomial ring. So just like you did z slash p, it became a field. For the same proof, you just have to copy paste the proof. And in this case, the copying is allowed. We won't consider it plagiarism. You just copy paste that proof and you will see that now fpx slash f will be a field. Okay, and the converse also you can prove similarly. So let's just write the main point. So main point here is consider an ax in fpx slash f such that ax is not 0 mod f, which is just saying that fx doesn't divide ax. So for any such ax, what you can do, I mean, we only have to show inverse, right? The addition is clear, multiplication is clear. Only thing that we have to show is when will an inverse exist. And we want it to exist always. So for this ax, to find the inverse, what you will do is apply Euclid's algorithm. So you will get some u times a plus v times f equal to, so what is the GCD? Maybe I should write the GCD first. What is the GCD of A and F? We have seen this before, right? If f is irreducible polynomial, GCD can only be 1 or 0. Well, A is not 0, so it will be 1. So that is what you get here. Right? You get from extended Euclid GCD, you get ux, vx, combination is 1. That's the inverse. So U is A inverse mod F. That's the only critical thing. Amongst the field axioms, the hardest thing is to show that inverse exists, and inverse exists here. Basically the same proof that you wrote for numbers. Now instead of Z, you will use Fpx, and instead of F being a prime number, you will say that it's a irreducible polynomial. And instead of saying a number Ax, you will say polynomial Ax, right? So it's just it's a simple copy paste of that proof. So this makes field, you get now more complicated fields. Yeah, but the question, well, any questions here in the proof, in the statement that I have written? So once you understand this, the question you should ask is, do such fields actually exist? Are they actually available in nature for you to use in computer programs? Which means that you have to find irreducible polynomials fx. Do they exist? Why? I mean, to show that prime numbers exist took you half a semester, right? Till the point we got to prime density, it was more than half of the semester. So you will have to spend probably similar amount of time to show that fx also exists, because it's a prime in this ring. But now we can do it in half a class. Okay, since you are now so well versed in abstraction, we'll now show that actually these fields exist. They are not just in definition. So how to find irreducible F? In Fpx. So this find is too much. It's also in your assignment 4, but first you have to answer whether they even exist. And we will do that. Okay, let me anyways make a remark that if they exist, then this Fpx mod F is a field of, oh, let me add degree also here. How to find irreducible F of degree D? So if they exist, then Fpx mod F is a field because of the previous property. What is its size? How many elements will it have? The residues after division you get is x to, it's a polynomial in degree d minus 1, right, because your modulus is degree d. So how many elements are there in degree d minus 1? Is a field of size p to the d, right, because the numbers are 0 to p minus 1, and in every coefficient you will put one of these, and there are d coefficients. So you get p to the d, just that simple calculation. And the characteristic of this field is, what is the characteristic? How many times do you add 1 to get 0? Come on, this is trivial. It has to be the same as Fp. Fp is there. So characteristic doesn't change. Right? So this will be your first field. If f exists, this will be the first field that you have seen where characteristic is p, because Fp is there. It's a subset. This object is a field and it is of size prime power. Right, till now you have only seen d equal to 1. So you don't even know about d equal to 2, but you will get all those constructions if you find this f. So we call this Fp to the d. Okay, so consistent with Fp notation, we'll call this finite field by this notation f sub p to the d. So this is a field finite, size p to the d, characteristic p, contains Fp. And till now you have only seen the d equal to 1 case, right? Now we want to go to d equal to 2 and any d actually. So that will be our next major theorem. Think of this theorem as existence of prime numbers. But before that, before going into the existence, let me make one more conclusion. So assuming it exists, what can you say about its multiplicative structure? Like for d equal to 1, we have shown Fp star is cyclic, right? There are a lot of primitive elements. Can you say the same thing here? So again, this is the proof is the same using the technique you are good at, which is copy paste. So you copy paste the proof of Fp star here. It will just work and it will give you that Fp star has phi to the p to the d minus 1 primitive elements. So the proof is just like we started with Fp d star equal to p to the d minus 1. And whatever we did in that proof, right, you just copy paste that here. I mean this 3-page proof. So for this theorem, whatever you did, same thing you can do, starting from the first line where Fp star is p minus 1. Now Fp d star is p to the d minus 1. Everything follows just like that. And what you will get is you will get in this case phi of p to the d minus 1 count. Okay, so this you can just repeat the proof. I will not repeat it because there is really no change. It is the same proof. I showed you the proof for d equal to 1, same thing works for d greater than 1. Because all that proof uses is actually these field properties. They are true for FPD also. Okay, so yeah, so in particular what this means is I should have said this before. There is also this property that for all A in FPD star, what can you say about A to the P to the D? It will be A, right? Just like for D equal to 1, A to the P was A. The same proof also gives you that A to the P to the D is A. It's again the same proof. Similar to this FP star. That's an important part in the proof of the above primitive element case. But anyways, it's important enough to be written explicitly here. So FPD star, whenever it exists, it has P to the D minus 1 elements, and any element, when you raise it to P to the D minus 1, you get 1. And there are elements A whose order is P to the D minus 1. That is what the theorem property above is saying. Yeah, maybe you are confused enough to see an example now. Let's do the example before we make it more complicated. So let's take the example of P equal to 2, right? You know what F2 is. Do you know what F4 is? What is F2 square? So let's consider the polynomial x square plus x plus 1 in F2x. So this polynomial x square plus x plus 1, is this reducible? Mod 2? Yes or no? If it was reducible, then it will have roots, and the roots can only be 0 or 1, right? You substitute 0 and you substitute 1 and you see that nothing vanishes. So this means that x square plus x plus 1 is irreducible. So since it is irreducible, now you have F4, which is F2x mod x square plus x plus 1. So this is your first interesting finite field. It goes above the prime field. Sorry. So the polynomial arithmetic modulo x square plus x plus 1 gives you how many elements? 4 elements, right? So this is 0, 1 is there because of F2. What else is there? X is also there and x plus 1 is there. Right? There are only 4 elements. Obviously, you can add any two and get a third one, and you can multiply any two. So multiplication has this interesting thing that x times x plus 1 is what? X square plus x, which is 1. right? Which means that x and x plus 1 are inverses of each other. So this is x inverse and this is x plus 1 inverse. Right, so you see the field explicitly. This is kind of extension of Boolean algebra, if you know this and or not. That only works on 0, 1, but now you can actually make it work symbolically on more elements. So here you have added x and its inverse will be x plus 1, but interestingly it's also x plus 1. Right, this is happening in a very tiny space. All these are related. Yeah, let us now see the properties that I have written above. What is a to the 4 here? Right, 0 to the 4 is 0, 1 to the 4 is 1, x to the 4 is? What is x to the 4? X to the 4 is x square whole square. What is x square? X plus 1 whole square. What is x plus 1 whole square? X plus 1 whole square is x square plus 1, which is x. Right, so the theorem I wrote, the property I wrote is indeed true. X to the 4 is x. And same thing you can do for x plus 1 also. X plus 1 to the 4 will also be x plus 1. Right, so you can manually check these things here. Finally, give me a primitive element in this finite field? Which element generates all three, 1, x and x plus 1? So it should have phi of 2 square minus 1, right, which is phi of 3 many primitive elements. There should be 2 primitive elements. So those two are, it's anybody's guess, they have to be x and x plus 1. So x and x plus 1 are primitive. Right, this you can check. X generates itself, then x square generates what? X square is x plus 1, and what is x cube? X cube is 1. Right, so order of x is 3, it generates 3 elements, and order of x plus 1 is also 3, it generates 3 elements. So these are the primitive elements. So whatever I have written above, I was not bluffing. Everything works, right? But the problem is, how will you find these irreducible polynomials f? Because here it was, I mean, I just gave it to you, but will it always be possible? So, yeah, so that's the question, whether they exist, and then how to find irreducible polynomials of degree d in FPX. So what we will show in the end, which we have to do tomorrow now, we have to show that, we'll show that for all prime p, for all d natural numbers, fp to the d exists. Okay, in other words, irreducible polynomial can be found. This is how we'll do it. we'll not only show the existence of fx, we'll actually count how many fx there are. Okay, we'll give you a count, which is also some practice exercises in the assignment, how to count irreducible polynomials of a certain degree. And once you have the count, you show that it's positive, they exist. Once they exist, the mod fx arithmetic will give you the finite field. Okay, this is how you find them and then use them in all sorts of algorithms in computer science. So let's define that count. So I of t will be the number of irreducible degree t polynomials in FPX. I could also have said IPT, but P I will suppress because we'll just think of a fixed prime P. So with that understanding, IT is just the number of degree T irreducible polynomials in the polynomial ring, mod P. And let us try to do this counting. Yeah, so we'll need more properties before we can even begin to count. So let me write this first. So let Gx be degree T irreducible. Then what can you say about x to the p to the t mod Gx? What do you think is this? I mean, since I want to go over all the degree T irreducibles, I want to count them, I want to prove some properties. So here I want to try to understand what is x to the p to the t mod Gx. Why is it x? Yeah, so this is actually just a rehashing of this second blue property. When irreducible G exists, you get the finite field p to the t, right? And x is an element there. So x to the p to the t will be x. That is the proof. You just have to invoke that property. So x is an element in Fpx mod G, which is a finite field of size p to the t, which from the previous property means that x to the p to the t is x. So x to the p to the t is x in the field, and which is the same thing as saying mod G arithmetic. Is that clear? So this simple property is highly useful because what this is saying is if you factor the polynomial x to the p to the t minus x in mod P arithmetic, what is the factorization? At least the degree T factors that you will get, they will all be irreducible. Or maybe that is too strong at this point, but at least it is saying that all the degree t irreducible polynomials gx, they appear in the factorization of x to the p to the t minus x. So this polynomial contains degree t irreducibles. Mod p. Okay, I mean obviously it is possible that x to the p to the t minus x doesn't have any degree t factor, which means that there is no degree, there is no gx. But if there is a gx, then it will divide ex. Right, so it's a good polynomial to have, and we will prove some powerful properties tomorrow.